This is lesson 2.6, solve compound inequalities. The learning objectives are to solve compound inequalities with the word and, solve compound inequalities with the word or, and solve applications with compound inequalities. In the last lesson, lesson 2.5, you learned the basics of solving linear inequalities. I'd refer you back to that lesson to make sure that you have those skills before you proceed. But if you've already got those skills, let's move forward. What is a compound inequality? A compound inequality is made up of two inequalities connected by the word and or the word or. All right, so we've got two options. We've got two inequalities with and between them or between them. So how are those two different? Well, to solve an and compound inequality, look for all numbers that make both inequalities true. And then to solve an or compound inequality, look for all numbers that make either inequality true. So the main words here are, an and inequality is where both inequalities are true versus an or inequality where either inequality is true. Let me explain a little better with these two comparison examples on left and right. All right, so if I had to find x is greater than -3 and x is less than or equal to 2, I would graph both inequalities. X is greater than -3 is graphed here. X is less than or equal to 2 is graphed here. And if the word and is between them, then the solution is just the overlapping shaded regions. So the only overlapping shaded regions on these two graphs are the values between -3 and +2. So that's what gets shaded. All right. Now, if instead we have the word or between these inequalities, then we shade all of the regions that are shaded on both of these number lines, right? So from -3 to infinity or 2 to -infinity, any blue stuff that's either here or here gets graphed on this compound inequality. And so it ends up being all of this line gets graphed, it all gets shaded, and it looks like this. So here is the compound inequality with and versus the compound inequality with or. These are the solutions for both of them graphically, and we see how they're different. All right, we're going to get more and more comfortable with this as we look at examples. So I'm going to show you these examples coming up. Now, here's a quick how-to step process for how to solve a compound inequality with the word and. Step 1, solve each inequality. Step 2, graph each solution. Then graph the numbers that make both inequalities true. Step 3, write the solution in interval notation. Great. So here in these examples that are coming up, these next 5 examples, we're going to solve the inequalities, then graph the solution, and then write the solution in interval notation. Great. So starting with example 2.61, I'm going to solve each of these inequalities separately, these linear inequalities. So to do it, I look at the first inequality and I add 3. Rewriting the inequality, I get 6x is less than 12. I now divide by 6, and I have solved this inequality where I found x is less than 2. Great. Now I solve the second inequality. So I subtract 9 from left to right. I get 2x is greater than or equal to -6. Next, I divide by 2. And lastly, I rewrite the inequality as x is greater than or equal to -3. Great. I have now done step 1, which was to solve each inequality. So I solved the first linear inequality, solved the second linear inequality. And now I'm going to graph each of those solutions. Here I have 2 number lines to graph the 2 solutions separately. Okay, so oftentimes it helps to graph these visually. So I go to 2 and -3. Okay, so this is 2, this is -3. How do I pick which one goes on the left and right? Well, the smaller value I would place on the left-hand side of the number line. -3 is the smaller value. And then positive 2, I would put further to the right as I'm comparing these two number lines. Right? So positive 2, definitely greater than negative 3. And so that helps you set things up visually. Now, to go ahead and graph these, x is less than 2 has an open dot at 2, and then we shade the region to the left. There we go. And then x is greater than or equal to negative 3. I have a closed dot at negative 3. And then I shade the entire region to the right. This is x is greater than or equal to negative 3. Now, the next part is to graph the numbers that make both inequalities true. Not either inequality, but both inequalities. So we saw that we have the word and between these two inequalities. So my goal is to look at where the shaded regions are overlapping in the two graphs I've created. Okay, so I'll do a little comparison with you. This region's not shaded, okay? And this region's not shaded on this graph. So where is the red stuff overlapping on these two graphs? They're overlapping between negative 3 and positive 2. Great. So I'm going to, on the final graph of the compound inequality, I'm going to place negative 3 and positive 2, and I will have a closed dot at negative 3, just like I did above. I have a closed dot. And then with positive 2, I have an open dot. And the only region that is overlapping, making both inequalities true, is this region in the middle. Okay, so this is the overlapping region for the two graphs that are above. So I'm now going to finish by writing the solution in interval notation. So a closed dot gets a bracket. So I start with a bracket, and I say the interval is from negative 3, and then I put a comma, and it ends at 2, and I put a parenthesis for the open dot. My interval begins at negative 3. It's a closed dot, so I put a bracket. It ends at positive 2, and it's an open dot, so I put a parenthesis. There we go. So this part, this is my final solution that I have. This is the result of the compound inequality. Let's try another. So this is example 2.62. I will use the same process. So I'm going to solve this linear inequality, the first one. I'll distribute the 3 into both terms here, and I'll get a 6x. Actually, you know what's even easier? Maybe I just divide 3 out. So I'm going to divide a 3 out here. Okay, and then I end up with a 2x plus 5 is less than or equal to 6, because 18 divided by 3 is 6. I didn't distribute because the only value I'm trying to solve for is this x right here. It's inside the parentheses, so I don't need to distribute the 3. I'm going to divide it to the other side. Now I'm going to subtract 5 from left to right. And I am left with 2x is less than or equal to 1. And now I'm going to divide by 2. And I now know that x is less than or equal to 1/2 is the solution to this inequality. Okay, let's now solve the second inequality. So the second inequality, I'll divide by 2. And I'll get x minus 7 is less than, well, negative 6 divided by 2 is negative 3. Now I'll add 7 to the other side, and I find out x is less than 4. Negative 3 plus 7 is 4. So I've solved that second inequality. Now let's graph these two inequalities on the above number lines. The smaller value I'll put on the left, and the larger value I'll put on the right. So for example, I see this 1/2 value. That's less than 4. 1/2 is less than 4, so I put 1/2 on the left. Let's make it a fraction that looks like that. There we go. And we put 4 on the right. And graphing x is less than or equal to 1/2, I would put a closed dot at 1/2, and I would graph everything to the left of it. So shading that whole region to the left, cleaning this up, this is what I get. Now, x is less than 4. That's the next thing I want to graph. And so I put an open dot at 4, and then I shade the region to the left. Great. And now, because the word and was between them, this word and right here, I want to see where these two shaded regions are overlapping. I stack them on top of each other so it's easy to see. All right. So the only place where both inequalities are true is from negative infinity to 1/2, right? Both of these are shaded all the way up until that region. And so my answer, I'm going to graph the answer below, the compound inequalities answer. I have 1/2 right here, and then I have a closed dot at 1/2. And then I shade the region to the left, and this is the solution. All right. And I'm going to write the inequality notation now. So it starts at negative infinity. Remember, we write interval notation from left to right on the number line. Right? I'm looking at the number line here from left to right, and we're starting at negative infinity, and we go to 1/2, and it's a closed dot, so I put a bracket at 1/2. There you go. So this is my solution to the compound inequality right here. I've graphed it, I've written interval notation, and I've solved the two separate inequalities. Let's try another. So when I see 1/3 times x minus 4 is greater than or equal to -2, and -2 times x minus 3 is greater than or equal to 4, I get out my solution strategies for linear equations. Right? And so jumping in here, the first thing I would do to solve this first inequality is add 4 from left to right. And I get 1/3 times x is greater than or equal to -2 plus 4, which is 2. And now I'm going to divide by 1/3. Please remember, dividing by a fraction is the same thing as multiplying by its reciprocal. So I could multiply by the reciprocal of 1/3, which is 3/1, on both sides of this inequality. And what happens in that case, when you multiply reciprocal fractions, they multiply to make 1. So this becomes a 1x. And that's greater than or equal to 2 times 3, which is 6. All right, so we've now solved the inequality. Looking at the second inequality, I would divide -2 first. Since the only variable value is in the parentheses, I'm not going to distribute this -2. I'm going to divide it out. Okay? And when you divide by a negative number across an inequality, your brain should tell you at this point, based on our last lesson, that we have to flip the inequality symbol's direction. So I now have x minus 3 is less than or equal to. Okay, I'm flipping the direction of the inequality because I divided by a negative number across it. And 4 divided by -2 is -2. Now I'm going to add 3 from left to right. And I'm left with a statement that says x is less than or equal to 1. I have solved my second inequality. Now I had the word and between these two inequalities. So I'm thinking of, the solution that is a solution to both of the inequalities in question. But let's graph both those inequalities separately so we can see what their overlap would be. So I take the smaller value and I put it on the left and the larger value on the right. I'll do x is greater than or equal to 6 on the top. So I go to the larger value of 6. And then on the bottom, I'm going to do x is less than or equal to 1. So I put the smaller value on the left. And now I have closed dots for both of them, right? close dots in both cases. And if x is greater than or equal to 6, I shade everything larger than 6 in this case. And if x is less than or equal to 1, I shade everything less than or equal to 1 in this case. All right, now that I've graphed both of these, I have a visual of what their overlap is. Where are these two graphs overlapping their shaded regions? And the answer is they're not. This section of shaded stuff doesn't overlap up there, and this section of shaded stuff doesn't overlap down there. And so the answer to this inequality is that there is no solution. That's the answer. Okay, so no solution to this compound inequality because there was no overlap of the shading of their two graphs. Okay, let's go back up and we're going to see things in detail. We have solved 3 compound inequalities with the word and we graphed the separate inequalities, right? We solved 2 inequalities, we graphed the 2 of them, and we looked at the sections in which those shaded regions were overlapping, and we wrote the answer. We did it again here, right? And we did it again here. And in this case, there was no overlap, therefore no solution. Great. Let's move forward in our notes. Now, the compound inequality with and can be written as a double inequality. So let's define double inequality. A double inequality is a compound inequality such as a is less than x, which is less than b. It is equivalent to a is less than x and x is less than b. All right, so it's a compound inequality, but we can write this compound inequality with the word and like this. And this is simpler. It looks simpler. We don't have to worry about the word and anymore. It's really nice. Now, there are different versions of this, right? I use the less than and less than version here and here. But we could have had less than or equal to symbols, and that would cause that to have less than or equal to symbols. Or one of them could be less than or equal to, and the other one's strictly less than, like this. And so I would have that. Or the fourth version would be this, so I'd have that. Okay, there you go. So we could have 4 varying versions of this compound double inequality. Let's look at double inequalities and see something cool that we can do with them. So here's a double inequality right here. It says -4 is less than or equal to 3x minus 7, which is less than 8. All right. And you know what's cool about double inequalities? You can do algebra on them. And when you do it, like, we want to get x alone. We want to get this x all by itself. And so the operations we think of is addition of 7 and division by 3, right? But what's cool is if we add 7, we do it to the 3 separate pieces in the double inequality, right? This is a piece, this is a piece, this is a piece. So we're going to take that addition of 7 and we're going to do it here, here, and here. And it gives us a result. -4 plus 7 is 3. And that's less than or equal to 3x. And of course, these -7 and +7 cancels, which we wanted. And we get that's less than 8 plus 7, which is 15. Next, we can divide by 3 on all 3 regions. And so cleaning up this inequality, 3 divided by 3 is 1, which is less than or equal to 1x, which is less than 5. All right, so I have solved this double inequality, and it looks like this now. I think that's pretty cool. And so this double inequality is really 2 inequalities in one. I've got, first of all, this part, which says x is greater than or equal to 1, and this part, which says x is less than 5. And so I can go and instead of writing the separate graphs and then combining them together like we did in the last 3 examples, the great thing about a double inequality is I can just look at the lower bound, which is 1 in this case, and the upper bound, which is 5 in this case, right? These are the bounds of the variable x. And I can look at the inequality symbols and say, well, The 1 should have a closed dot, and the 5 should have an open dot, right? Because less than or equal to symbol here will be a closed dot. Less than symbol there is an open dot. And x, the variable, is all the values between them. And so I'm going to shade this region as my solution of the graphing. And now I'm going to write this in interval notation. Writing it in interval notation, I would have a bracket. Let's make this skinny. A bracket with 1, and it goes to 5, and that's a parenthesis because it's an open dot. And we're done. So double inequalities are great. You can do algebra on them, like here I added 7 on all 3 pieces. Here I divided 3 in all 3 pieces, and I got my result. Now you'll remember that if you multiply or divide by a negative number across the inequality symbol flips. And if I was to be dividing by a negative number like -3 here, here, and here, it would flip both inequality symbols to the opposite direction. Okay, so if you're ever dividing by a negative number across a double inequality, flip both the inequalities directions. Great. So up to this point in our lesson, we have been working with compound inequalities with the word and. Now we're going to switch and solve compound inequalities with the word or. Okay. Step 1, and this is how you do it. Step 1, solve each inequality, just like before. Step 2, graph each solution, just like before, but then graph the numbers that make either inequality true down below. Okay, now step 3, write the solution in interval notation. Let me show you how it all works. So first, looking at my 2 inequalities, I'll solve them one at a time. I'll subtract 5 from left to right. And I get -3x is less than or equal to -6. Now I'm going to divide by -3 across the inequality. You'll recall we need to flip the inequality sign. And now we could take -6 divided by -3 to make +2. Okay, I have solved the first inequality. Looking at the second inequality, I'm going to first subtract 8 from left to right. Rewriting it, I get 2x is less than or equal to -3. Next, I'm going to divide by 2 across the inequality. And so I'm left with x is less than or equal to -3/2. There's the solution for my second inequality. And so now we could graph each one separately. Pick the smaller value to go on the left and the larger value to go on the right. So, my first inequality here is x is greater than or equal to 2, and 2 is a larger number than -3/2, so I'm going to put 2 on the right-hand side. Okay, boom. And then for my second inequality, x is less than or equal to -3/2, I put -3/2 on the left-hand side, because it's smaller than 2. All right, now I'm going to put closed dots for both of them. So I have closed dots at those locations. Next, I'm going to graph everything larger than or equal to 2, like that. And I'm going to graph everything less than or equal to -3/2, like that. Now here's where the word or comes into play. Because this was an or inequality, here's the word or, we graph the numbers that make either inequality true, not both, just either inequality. And so every shaded region that we have in both inequalities drops down to our final solution. Okay, so I'll show it to you. I take the -3/2 and the 2, and I had a shaded region from 2 going to the right forever. And I had a shaded region from -3/2 going left forever. Right? And so all I'm doing is I'm dropping down my shaded regions for the first solution and the second solution, and this becomes my new solution set for the compound inequality with OR. All right, now I'm going to write the interval notation. Notice we have two separate pieces of shaded regions. So my interval notation starts from the left, negative infinity, and it goes all the way until negative 3/2, and it's a closed dot, so I put a bracket. Now, the next piece is 2, starting at 2, and it goes to infinity. So it looks like that. So I've written this shaded regions piece as that interval notation, this shaded regions piece as that interval notation, and now I just put a union symbol between the two intervals. The union symbol is saying, hey, these two intervals are actually being combined together from my solution set. They're two intervals combined together. So don't forget to put the union symbol when you answer these questions. Great. Moving forward, let's go ahead and look at the next example. And it's an OR example again. Yes, I have two inequalities with the word OR between them. So starting again, I'll solve the first inequality. I'll do it by adding 4 first, from left to right. Rewriting my inequality, I have 2/3 times x is less than or equal to 7. Now I'll divide by 2/3, but remember, dividing by a fraction is the same thing as multiplying by its reciprocal, which is 3/2. So whenever I divide by a fraction, I remember, hey, it's easier to just multiply by the reciprocal. Because reciprocals, when they multiply together, they cancel, right? This 3 cancels this 3, this 2 cancels this 2. It results in just 1. And so I have 1x. And that's less than or equal to, well, 7 times 3 is 21/2. So I have 21/2. It's good to write it like this. You could also write it as 10.5. It doesn't matter. If it helps you know where that 21/2 is on the number line to write it as a decimal, go ahead and do it that way. Okay, now looking at this second inequality here, I want to solve for x. It's inside the parentheses. It's the only variable. So what I'm going to do is divide by 1/4. And dividing by a fraction is the same thing as multiplying by its reciprocal. So I'm going to multiply 4 here and here. Okay, so those 4's cancel. And so I get x plus 8 is greater than or equal to -4. Now I subtract 8 from left to right. And I find out x is greater than or equal to -12. I have solved this inequality. All right. Now, which number is bigger, which one's smaller? Well, -12, that's negative, so it's smaller. So the second inequality that has -12, I'll put it on the left. And then the first inequality, which has 21/2, which is 10.5, it goes on the right. I'll write it up above. Okay, and I'll write the fraction like this so it fits. Great. Closed dots or open dots? Well, closed dots, right? Because of the less than or equal to sign or the greater than or equal to sign. Okay, now where do I shade? Well, x is less than or equal to 21/2, so I'm shading the stuff to the left of it. And x is greater than or equal to -12, so I'm shading the stuff to the right of -12. And now I ask myself, okay, what is going to be the final solution? And I say, well, all I have to do is drop down all the solutions to the bottom, all the solutions of the first inequality and all the solutions of the second inequality. And then I notice something. That would mean that my entire graph is shaded. Forever left, forever right, all of the regions of the graph are shaded. This means that the solutions are all real numbers, right? So this is my answer. Like, it's all real numbers are solutions to this compound inequality. And if I write all real numbers in interval notation, well, they start at negative infinity and they go to positive infinity and there's no break. So that's the interval notation, negative infinity to infinity. Great. And we have one less problem, and it's an application problem with compound inequalities. So let's give you some context. Real world context here. Due to the drought in California, many communities have tiered water rates. There are different rates for conservation usage, normal usage, and excessive usage. The usage is measured in the number of 100 cubic feet the property owner uses. Yeah, so California, it has interesting laws where, sometimes the price is priced as conservation usage. Sometimes the price is different, is normal usage. Sometimes excessive usage. So they'll change the price on their residents. Pretty cool, or not cool, however you want to think of it. Anyway, um, looking at the example 2.67, let's go ahead and jump in there. And it says, during the summer, a property owner will pay $24.72 plus $1.54 per HCF. Right. And by the way, that's 100 cubic feet, right? HCF. It was defined up above for normal usage. Okay, so this is the rate for normal usage. But the bill for normal usage would be between or equal to $57.06 and $171.02. How many HCF can the owner use if he wants his usage to stay in the normal range? Great. So to set this up, we were given a lower bound and an upper bound. All right? And we were given some extra information. So I'm going to set it up for you. I'm going to say the lower bound is 57.06, which is less than or equal to $24.72 plus $1.54 times X, where X is the amount of 100 cubic feet, HCFs, right, that the property owner uses. And now I'm going to set that less than or equal to my upper bound of $171.02. Okay, so I've created a double inequality. They gave me a lower bound, they gave me an upper bound, and my rate, what I have to pay, this plus this times the HCFs is what goes in between them. Okay, great. So this is my starting point. And I want to solve this double inequality for the variable x. And so remember, we can, do things like subtract across the double inequality on all the sides, like here and here. So I'm subtracting 24.72 from 3 different locations, here, here, and here. And I'm going to write my result. That result is $32.34 is less than or equal to $1.54 times x, which is less than or equal to $146.30. Great. So now that I've subtracted off that $24.72, I now have this inequality that results. And now to get x all the way alone, I need to divide by 1.54, $1.54, and I'm going to do that in all 3 regions, like this. Great. And so taking this 32.34 divided by 1.54 gives me 21. Comes out nice and clean. I got a 21, which is less than or equal to x, right? Because 1.54 divided by 1.54, that cancels, so I just get x, which is less than or equal to 146.3 divided by 1.54, which is 95. Okay, so here's my final result. So what does this result mean? It means the owner can use between 21 and 95 HCF, right? 100 cubic feet of usage of water. So I'll write that. The owner can use between 21 and 95 HCF. And we have concluded this set of notes. Thank you. This lesson was a great one for learning more about inequalities, and specifically compound inequalities, which use the word and the word or. Have a wonderful day. Thank you.